Hey, so welcome to another episode of ICT. So this episode I'll be focusing on logic gates, right? So what are logic gates? Well, logic gates are basically switches. It's basically the most fundamental component of a computer or electronic system, right? So a logic gate is basically a switch, right? A switch basically is nothing more than a piece of circuitry which enables or disables or is open or closed and allows electricity to flow through. So it is a fundamental component of an electrical circuit. Right. So when it comes to, I think you have already done these, and if you look at your grade 6 syllabus, you would probably have done simple circuits like series, how to connect a battery in series or in parallel, how do you increase voltage, how do you increase amperage. Now those kind of things are there, so you are not completely new to electronics. Right, so what I'm going to show you today is, when it comes to logic gates, it's basically, just think of them as transistors. Okay, so I have a box full of transistors here. So if I look at a single transistor is this small little thing over here. So that has 3 wires or 3 pins, right? And that's what a transistor looks like. Okay, right. So that is very, very small. It's extremely small, right? So they used to do this. What they used to do is, so scientists who are building calculators way back in the 1960s, right? They used to build these calculators using transistors, right? And it was really, really bulky, because when you consider a transistor, it's, although you see it as a small thing, it is huge compared to the modern technology. Right? Transistors way back in the day in the 1960s were massive, right? And if you go back to the 1950s, it's even larger. It was a vacuum tube, which is about that big. Unfortunately, we don't have vacuum tubes. I don't have any vacuum tubes. Uh, Otherwise, I could have shown you what a valve vacuum tube looks like. So today we just have these small transistors. So transistors are basically a fundamental component that allows electricity to flow in one direction based on certain given inputs. So let me first reduce this right over here. Right, so what we're going to learn here is basic logic gates. So there are 2 types of logic gates. You have the basic logic gate and you have a combinational logic gates. Now combinational logic gates are basically basic logic gates which have been combined with another logic gate, right? Like if you take now these transistors, like for example the transistor that I showed you, it takes in 2 inputs. It takes in 2 inputs and it sends out a single output. That's how a logic gate works. Some logic gates might even take in, like the modern logic gates in certain microprocessors that are built for AI, sometimes might take in 3 inputs. And based on those multiple inputs, you will get an output, right? But most logic gates are having 2 inputs. Okay, so you have basic logic gates, like you have the AND logic gate. I will show you what an AND. Then you have the OR logic gate and you have a NOT logic gate. So that's how it basically takes in 1 or 0. Basically 1 or 0 simply means whether there's electric current flowing or not flowing. So let's look at it. So let me go back to my presentation, right? Okay, so basic logic gates. So you have main gates and you have combined gates. So a main gate is basically, as I said, it's like a switch. So if I take a switch, okay, let me show you if I take a switch, right? So the basic switch is this. That's the most basic switch I can think of, where you have a switch. When you turn it on, the light bulb lights up. It's that simple, right? So this switch is currently open. So in an open state, no current is flowing. But when you have a switch closed, then the current flows through and creates a circuit, and then the light starts to light up. Now you have learned this in, I think, grade 6, grade 7, grade 8, grade 9. It's all there. So in grade 10 only you get logic circuits, where you take the same switch and make a truth table, right? So you would combine this with algebra. So when you combine that with algebra, you will get something called Boolean algebra, right? But it's the same concept, but we're going to add a layer on top of that, and we are going to use algebra as equations. Okay, so if you look at this simple switch, now what is an AND switch? An AND switch is basically when you have two inputs, both inputs need to be satisfied. That means both inputs should be true for the light to work, right? So if a light bulb is to light up, you need to switch on a switch and a B switch, both. That is what you call a AND switch, right? So let's go back again to our AND switch. So our AND switch, when we consider the two inputs, both inputs need to be conditionally true, right? So both inputs, when it comes A and B, will return, the output will be X. So in Boolean algebra we say it's A dot B. So A dot B simply means both conditions have been satisfied, or rather maybe they are not satisfied, but either way those are variables. So the Boolean algebra for that is A dot B, right? That's one of the main gates. So we have to remember. Now personally I find it difficult to memorize things, so therefore I have to create my own things using my hands. So I write a lot, I create a lot, I design systems, or I'll simply use a transistor and I'll make my own AND gate, right? So building an AND gate out of transistors, it's not that hard. I can't find my AND gate. I built it when I was going to school, so I had no idea where it is now. But I'll find it and I'll show you what an AND gate looks like, right? So an AND gate is basically, it takes in two inputs, and when both inputs are true, the output will be true. But if one of the inputs are false, or both inputs are false, output will be false. So only condition where it becomes true, where this X becomes true, is when A and B are both true. That's why it says AND, right? When A is true and B is true, only X becomes true. So let's look at the next main gate. Next main gate is an OR gate, right? That is also same transistors, okay? But the transistor, the way they are connected, the way the pins are connected might be different, right? So in an OR gate, one of these conditions or both the conditions can be true. In that case, it's an A plus B. That's how you represent it in Boolean algebra. It's A plus B. This is an A dot B. This is A plus B for an OR gate. So if one of these conditions or both conditions are true, at least one condition is true, the X is true. That means the output is true. And then finally you have a NOT gate. So it basically negates whatever you send in. So if you have 1, the output becomes 0. If you have 0, the output becomes 1. That's why it's a NOT gate. Now, this is the thing. This NOT gate is a triangle with a circle, okay? I can combine this NOT gate with an AND gate, okay? If I combine the NOT gate with an AND gate, I will convert that into something called a NAND gate. So a NAND gate is the same as an AND gate reversed, or rather negated, the output negated. So in an AND gate, let's say you got 1 and 0. So it's 1 and 0. Since it's AND, it's coming as false because both conditions have to be true for you to get a true. So if you get 1 and 0, this becomes true, right? So remember this, sorry, if you get 1 and 0, this is false. Right? So in here, in the NAND gate, if you consider A and B as 1 and 0, remember the AND gives you 0. So in here, the 0 becomes 1. So that's why it's an A dot B bar. So whatever you get from the AND gate is negated. So if you have 0 and 1, if it will become false, then that becomes true over here, right? Then if you have 0 and 0, that's also 0, but it gets negated to 1, right? But if you have 1 and 1, remember this is it's giving you 1 as a standard AND gate. Since it's an AND, since this is an AND gate, that 1 becomes 0. So in this, you will have in most conditions for this for the input, you will have most of it is coming as 0, but in here most of it is coming out as 1, except for one condition. Right? Okay, so let's look at the next one. This is a NOR gate. That's an OR plus a NOT. Same as an OR gate. If one of these conditions are true, the output is true, but it's negated in here. Right? So let's look at a truth table. For example, let's look at this truth table here. This is an AND gate truth table. And an AND, right? So guess what? If A, now this is how you draw an AND gate, right? So this is how you draw an AND gate. It's like, you have a straight line and then you have this, curved. OR gate, you have this quarter moon. It's a quarter moon shape. Okay. And this is a knot, is a triangle and a circle. So here I'm going to see what a truth table looks like. Truth table basically will have A and B. So it's A and B. It's like this. It's 2 to the power of. Now you have A and B. That's 2, right? So 2 to the power of 2 will generate 4. So you have 4 conditions here. If you have 3 inputs from here, then it's 2 to the power of 3. Okay. That means it's what? 2 to the power of 2 is 4. 2 to the power of 3 is 8. So you will have 8 combinations if you have 3 inputs. So if you have 4 input, then it becomes 16 combinations, right? But if you have only 1 input, that's just only 1 combination. We have 2 to the power of 0. Oh, sorry, 2 to the power of 1. So 2 to the power of 1 will give you either 1 or 0. Right, so let's look at it here. So it's A and B. If A and B is 1, then this becomes A dot B becomes 1. If A and B is 0, A dot B is 0 because both conditions have to be satisfied in an AND gate, right? So 0 and 1, 0 and 0, all of these are not producing 1 as an output because only the first combination of 1 and 1 produces 1. So that is why it's like this. Now, if we go into the NAND gate, it's the complete opposite, right? Which means the 0 becomes 1 and the 1s become 0. So all of these zeros turn to 1 and this 1 turns to 0. Okay, right. So that's how it works. So here, if you try to look at it, for example, now this one, it's here again, it's an AND gate. I showed you earlier how an AND gate works. So here, how would I do it? Remember, it's an AND gate. For this circuit to work, both switches have to be on. So which means if both switches here, this is a truth table, if both switches are on, the light lights up. So that means it's 1. Okay, that's a true statement. But if only one of the switches are turned on, but the first one is turned on and the second one is not, that light is not going to light up. What about the first one is turned on and the second one is turned off? Still not going to light up. Both are turned off? No, still not going to light up. That's how you build a truth table. So truth tables in ICT, they will come continuously. So if you pursue ICT even into your career path, into your degree program, into A levels, the truth table will always be there, right? You can't get away from it, right? It's just like flow charts. You can't get away from it. So you have to basically continuously use flow charts. Even if you do even accounting, if you leave A levels and start doing accounting or business management, you still have flow charts. Now you may not have truth tables in those, but when it comes to ICT, you will always have a truth table. Even in project management, if you're doing programming, truth tables will always be there because you need to identify, because combinations, especially when you're dealing with circuits or when you're dealing with Internet of Things, which are small devices that you can connect to a computer and get them to control or get input from sensors like thermometers and hygrometers. So you have digital devices, digital sensors where you can connect. So all of those basically will have truth tables. When you're building something, you need to have a truth table to see whether what you built is valid, right? Okay, so this is how you basically now this is a combination of multiple gates, right? So you have AND gate, NOT gate, OR gate. So this is something that you will get for your exams, right? So next year when you're doing O levels, this is something that you will get, right? All of these are logic gates that will come for your exam. You will get around 3 to 4 questions on logic gates when it comes to MCQ. That is guaranteed. Okay, so let's get back to our logic gates, right? So when it comes, okay, so now we basically we did the basic logic gates. So let's look at combining logic gates, right? All right. Okay, here we go. Let's do something like this. Let's combine logic gates. Now, as I said earlier, you will have a situation where you get 3 logic gates, logical inputs to a single gate. Okay, so let's look at this. This is an AND logic gate, right? So an AND logic gate has ABC. Okay, given the below is an AND logic gate with 3 inputs, A, B, C. The above AND logic gate is an equivalent to the circuit given below, right? So write down P, which is the output of the AND logic gate for A dot B inputs, which is the output of the, okay, write down the Q, which is the output of the AND logic gate for P and C inputs. the value of Q is equivalent to the output of AND logic gate, which means, okay, so if I draw this, okay, so right, so we have the A and B inputs and the output is a P. If I do a truth table, okay, so A, B and P, this is how, remember, since there are two inputs, you will have four combinations. So that's 2 to the power of 2. That's 4 combinations. So I will start with 0, 0, 0, 1, 1, 0, 1, 1. That's how the combination. So you can put 0, 0, 1, 1 and then 0, 1, 0, 1. You can do it like that. And then here we go. Because this is an AND gate, both conditions need to be true. Okay. So 0 and 0 is obviously false. So false and true, false, false. And this is the only condition where it becomes true. Right? Okay, next one. Now let's take the C input. Okay. Okay. I'll just draw another AND gate and send C input. Let me draw properly that line. Right, much better. C input. And this is the Q. Right. For the Q, we need to add P's output, which is here, and C. So we need to put P and C. So here we go again. We put in 0, 1. Wait, we have to put in here also 0 and 1. Okay, we have to basically fill out these values 0, 1, 0, 1. Okay, right. So here you have this one, Q. So we have P and Q 0, 1, 0, 1. We have to keep on repeating. So you have 0, 0, 0, and only 1. So here the condition is all inputs need to be true in order for this Q output to be valid. Okay. Or rather, this output needs to become true. So that means all inputs A, B, and C all need to become true in order for the Q's output to also be true. Okay, the value of Q is equivalent to the A and B's input and C. So what's going to happen? Q is A, B, C. So if I am getting like this, right, A dot B is the output of that P, right? Okay, A and B is the output of P. Then C dot P is the output of Q. So C and P is the output of Q. Then A, B, and C is the output of Q. Right? Why? Because I'm going to substitute A and B here. So it's A, B, C. Okay. So that's how we can now, I showed you how to build a truth table. So here we go. There are 8 states in the truth table related to the above circuit, as there are 3 inputs. There are 8 states, so that's 2 to the power of 3. Right. Next one. Here we go. So you have 8 combinations for this. Right. So when you're building an A, B, C truth table, you have 8 combinations. Otherwise, you will only have four combinations. So in this diagram, I have put only four combinations because I already calculated the value of P. Now, because I already have calculated the value of P, right, I have a combination from the first four. Since I already have a combination truth table from the first four combinations, I can now just only put C. So I'll only have, I can just, just maintain this. So the combination here is for P, okay? It's not for AB, it's only for P. But if I consider A, B, and C, then yes, I have to put in the entire 8 rows of combinations. Okay, so let's look at the OR gate now. So here we go. This is an OR gate. Let's draw some OR gates, right? Okay, so you already have seen that, right? Okay, let's look at, okay, first, how do you draw the AND gate? You just put a line like this and then a semicircle, and then you have the two lines, right? So if we take a OR gate, it's a half a moon. Okay, that's not that good. Let me try it properly. Yeah, that's a little better. Right, so it has two inputs and an output. So the input would be A and B. Output is P. So in this, you would look at the A and B inputs like this. Let's say A is 1 and B is 0. What would be the output from P? Output from P would be, let's see, output from P is equal to this A or B. So A or B is basically one of these two inputs should be true. So if one of these inputs are true, then P is true. So in this one, A or B is true, P will become true. That is how P is true. So it's one of these conditions. When it comes to the AND, remember this AND, both conditions need to be true. Then only the output is true. So both conditions need to be 1 and 1. But in or only one condition can be true. But if both are false, then P is also false. Okay. That's how the OR gates work, right? So an OR gate is basically, if I try to draw it, let's say with a circuit. I'll put the battery here. And let's say, okay, that's the circuit. I will need to put in two switches. Like this, okay? Oops, that's not right. You have to put in two switches like this. Right. Now, in this switch A or switch B, if one of these switches are activated, guess what? Only one needs to be on. So if one is on and the other one is off, guess what? This will light up. If both are on, it will still light up. But if both are off, then it's not going to light up. So that's how an OR switch or logic gate works. Okay. So the truth table for this, if we draw a truth table, you will have A, B, and output P. Okay, draw a truth table. Starts from 0, 0, 1, 1, and then 0, 1, 0, 1. Right. So let's look at this. It's an OR gate. Okay. So only one condition needs to be true. So the only condition here that is false, right, is only these two. So both are false. So therefore P is false. And for all other combinations, at least one is true, which means all are true, like that. So what we have here is an OR gate, OR condition, either this or that. Right. So we have that now. So now how do we look at something like a NOT gate? Now that you know what an OR gate is, right? You also know how to draw an OR gate. It's a half moon shaped thing like that. Need to draw it properly. Like that. Okay. Right. Let me see, is this right? Much better. Okay, so there you have a terrible looking OR gate, right? So here we have to put in A and B as the inputs and P as the output. Okay, right. Now that you know what an OR gate is, let's look at the something called an NOT gate. Okay, so NOT gates are basically an easy way of it's basically like a short circuit, right? So NOT gate, I would, oops, wait, let me remove that also. Right, okay, so NOT gates is a triangle with a circle, and it only has one input. So the input that you get is, let's say A, and the output that you get is P. So in here, what we do is we say the output is not actually P, but rather the output from this is A bar. The output of that is an A bar. The reason why the output is an A bar is when we negate something, when we say it's the opposite of, we say it's a bar. So in this one, it's A bar. So when you send 1, it becomes 0. If you send 0, it turns to 1. Okay, so that is how this works. It's a NOT gate. Now, if I try to draw this NOT gate in like a circuit, it will be something like this. Put a battery. Okay. You have your bulb. Now, this one is always on. Okay. So, when you say not, that means the switch has to be turned on for it to be not on. Right? What you do is you put a switch here. It's like that. That's a not circuit. So when the circuit is open, the light is on. When this circuit, right? And when you close the switch, the light goes off. Why? Because it's a short circuit, right? So the electricity will flow from here, go like this, come out from here, and then go back again. Of course, you kill the battery immediately if you do that, but that's how a NOT gate is represented, right? So only when you open this switch, only the light comes on. Okay, superb. Let's draw some OR gates, right? Okay, so you already have seen that, right? Okay, let's look at, okay, first, how do you draw the AND gate? You just put a line like this and then a semicircle, and then you have the two lines, right? So if we take a OR gate, it's a half a moon. Okay, that's not that good. Let me draw it properly. Yeah, that's a little better. Right, so it has two inputs and an output. So the input would be A and B. Output is P. So in this, you would look at the A and B inputs like this. Let's say A is 1 and B is 0. What would be the output from P? Output from P would be, let's see, output from P is equal to this A or B. So A or B is basically one of these two inputs should be true. So if one of these inputs are true, then P is true. So in this one, A or B is true, P will become true. That is how P is true. So it's one of these conditions. When it comes to the AND, remember this AND, both conditions need to be true. Then only the output is true. So both conditions need to be 1 and 1. But in or only one condition can be true. But if both are false, then P is also false. Okay. That's how the OR gates work, right? So an OR gate is basically, if I try to draw it, let's say with a circuit. I'll put the battery here. And let's say, okay, that's the circuit. I will need to put in two switches. Like this. Okay. Oops, that's not right. You have to put in two switches like this. Right. Now, in this switch A or switch B, if one of these switches are activated, guess what? Only one needs to be on. So if one is on and the other one is off, guess what? This will light up. If both are on, it will still light up. But if both are off, then it's not going to light up. So that's how an OR switch or logic gate works. Okay. So the truth table for this, if we draw a truth table, you will have A, B, and output P. Okay, draw a truth table. Starts from 0, 0, 1, 1, and then 0, 1, 0, 1. Right. So let's look at this. It's an OR gate. Okay. So only one condition needs to be true. So the only condition here that is false, right, is only these two. So both are false. So therefore P is false. And for all other combinations, at least one is true, which means all are true, like that. So what we have here is an OR gate, OR condition, either this or that. Right. So we have that now. So now how do we look at something like a NOT gate? Now that you know what an OR gate is, right? You also know how to draw an OR gate. It's a half moon shaped thing like that. Need to draw it properly. Like that. Okay. Right. Let me see, is this right? Much better. Okay, so there you have a terrible looking OR gate, right? So here we have to put in A and B as the inputs and P as the output. Okay, right. Now that you know what an OR gate is, let's look at the something called an NOT gate. Okay, so NOT gates are basically an easy way of it's basically like a short circuit, right? So NOT gate, I would, oops, wait, let me remove that also. Right, okay, so NOT gates is a triangle with a circle, and it only has one input. So the input that you get is, let's say A, and the output that you get is P. So in here, what we do is we say the output is not actually P, but rather the output from this is A bar. The output of that is an A bar. The reason why the output is an A bar is when we negate something, when we say it's the opposite of, we say it's a bar. So in this one, it's A bar. So when you send 1, it becomes 0. If you send 0, it turns to 1. Okay, so that is how this works. It's a NOT gate. Now, if I try to draw this NOT gate in like a circuit, it will be something like this. Put a battery. Okay, you have your bulb. Now this one is always on. Okay, so when you say not, that means the switch has to be turned on for it to be not on. Right? What you do is you put a switch here. It's like that. That's a not circuit. So when the circuit is open, the light is on. When this circuit, right? And when you close the switch, the light goes off. Why? Because it's a short circuit, right? So the electricity will flow from here, go like this, come out from here, and then go back again. Of course, you kill the battery immediately if you do that, but that's how a NOT gate is represented, right? So only when you open this switch, only the light comes on. Okay, superb. Okay, so let's look at the combined gates. So the combined gates, as I said, the combined gates are a combination of main gates, right? So you can have the AND gate combined with a NOT gate will produce a NAND gate. Then you have an OR gate combined with a NOT gate, you will have a NOR gate. So how does a NOR gate or a NAND gate work? So let's look at it. So the AND gate, when coupled, okay, that's a terrible looking AND gate. Right, so the AND gate, right, that's better. When coupled with a NOT gate, right, is what you call the NAND gate, right? Okay, so what we are going to do is, instead of putting this whole thing, we can do something like this. This is basically the same gate which is there above. It's a NAND gate. So it's NAND, so which means if we write the truth table, okay, so if I'm going to do the truth table, I will say A, B, and output of X. Okay, so 0, 0, 1, 1. 0, 1, 0, 1. So we are trying to get all the possible combinations. Okay, right. Then X output will be the combination, that means the AND combination of these two, which means A plus A dot B negated. So A dot B. So this is actually A dot B, or A multiplied by B negated. Okay, so we can multiply even these two. That is the most easiest way. So let's multiply these two. What you get is 0, 0, 0, and 1, right? But that we need to negate. So therefore, we can't use that same thing. We'll have to use the opposite, which means since this is a negation, right? It's A dot B bar. You'll have to negate it. So 0 multiplied by 0 is 0. Opposite of 0 is 1. 0 multiplied by 1 is 0. Opposite of that is 1. Here again, 0 multiplied by 1 is 0. Opposite of that is 1. 1 multiplied by 1 is 0, is 1. Opposite of 1 is 0. So that's your truth table for the NAND gate. Okay, so it is extremely easy once you just sit down and start writing these equations. It's basically like I said, multiplication. Just simply multiply and negate it. that's for an AND gate. OR gate, you can, it's either this or that. So let's look at again a NOR gate. So NOR gate is, again the symbol for NOR gate is half moon. Okay, let me redraw that. Right. Okay, and the NOR gate has a small circle. So that is a NOR gate. So the truth table for that is A and B, and output of that is X. Okay. X is basically again A plus B bar. So again 0, 0, 1, 1, 0, 1, 0, 1. Those are the possible inputs. Right. So let's look at this. If it's an OR gate, that means this or that, then it produces a value of 0 because it's both of them are false. But we are going to negate it. So once we negate it, it becomes 1. Right? Okay. So it's again, next one, 0 or 1. One of these should be true for an OR gate. So that means this value is true. But since it's an OR gate, it becomes false. Right? Same with this. For an OR gate, it's 1 or 0, which means it's true. One of these has to be true. So it's true for an OR gate. But since it's true, this is a NOR gate. We invert that value and make it false. Right? Because it's invert again. Okay, so this one is 1 or 1. 1 or 1 is again true. We negate it, we make it false. Right? So that is how we do a NOR gate. Okay, right. So that's it. Now what we can proceed is we can do a couple of, I have created a PDF. You can download that PDF. I have also added a whole lot of questions in there. You can download, print it, and you can do it. So the only way to improve on logic gates is to do a bit of practice questions, right? So you have to go through your book. Where is that book? Here it is. And identify certain questions. For example, there are a couple of questions in here. Like there's an activity in here. What will be the logic gate output of Q when A, B, and C inputs are provided? Okay. Now this one is a NOR gate. As you can see, there's a small circle here. See, there's a little circle right here, which means there is a NOR gate, right? So NOR gates are built, in this particular case, it's 2 ORs and a NOT at the end, right? Same with an NAND gate. If you have like an input like this, let's say you have a NAND gate that has 3 inputs. A, B, and C. How do you get that? Right? So A, B, and C would simply be an AND gate here, and the output is channeled into another AND gate, right? So that's A, B, and this is C, right? The combination of that. And then from here, it's channeled into a NOT gate, which breaks it out, which basically negates the value. So you have the value of this coming from here. If we say that's X and then X and C comes out from here, and then it turns into a NOT. So that means it comes as A dot B from here, and then it recombines into this to become C, and then when it comes out from here, it becomes a NOT. So that's how you get that value A dot B dot C for a NAND gate. Okay, but this is a NOR gate, which means there are again two OR gates with a NOT gate. Okay, right. So if you or any of you have any questions, you can always message me, or you can just give me a call, or you can look at all the free video tutorials that I have, or you can even join any of my classes. There are so many ways you can learn about these OR gates, rather logic gates, and you can actually ace your exams. When it comes to the O levels, there will be definitely about 3 to 4 questions, MCQ questions on gates. Okay, definitely you'll have MCQs, and you might get an essay type question on a NOR gate, or sorry, logic gates. I'm looking at this NOR, that is why the NOR is coming out. So you can definitely guarantee to get a couple of questions, essay type questions on the exam when it comes to logic gates and Boolean algebra. Okay, so that's it for today's class. If you have any questions, just message me. You can contact me via chat, or you can join any of my WhatsApp channels. Okay, then I will see you around. Have a nice day. Bye bye.